The work we're going to present today is called You Only Scale Once, Efficient Text Detection Using Adaptive Scaling. It's a joint work with a bunch of great people, Tomer Ronen, Niv Giron, Tzach Avraham, Alon Palombo, and Yaniv Azar. Okay, and basically it's kind of a nice trick we wanted to share with the community. Okay, so what is text detection? Okay, so nothing surprising here. Text detection is basically the problem of taking an image, okay, and trying to localize all the text inside that image. And like many other problems in computer vision, it has come a long way in recent years, okay, going from more constrained, focused scenarios to really in the wild cases, okay? And I mean, it might seem like an easy problem on a first glance, but it's actually a pretty challenging problem. And there are many reasons for that. I want to share kind of the main key reasons, okay? So first one is scale variability. So if you look at the image on the bottom left, okay, you can see the word Guinness written in large letters, okay? It's pretty easy to detect, and actually something from the very kind of easy ICDR 13 benchmark. But if you look closely, okay, you have to believe in that, the word Guinness actually appears two more times in this image in the bottom left corner, okay? And handling this kind of variability is exactly what makes text detection challenging, okay? We're going to talk about that. Now, another challenge in text detection is the density. So if you look at the small region of text here, there's actually a lot of text there. And the problem in text detection is that we don't want to localize just, hey, there's text here. We want to localize every word on its own, okay? And one of the reasons for that is that text detection is usually done as a pre-processing step for text recognition, and text recognition works better when we have a single word in every bounding box. So this means that what we have here is actually a set of very small objects, okay, which are very close to one another. And localizing them, separating from one another, is very difficult. And the last thing, which actually is not the focus of our talk, is irregular shapes, okay? So working with not only bounding boxes, but also polygons and rotated shapes is more difficult. Okay, so hopefully I've convinced you that text detection is interesting and it's not really easy to solve. The next question is probably how do you solve it? And that's actually not the topic of today's talk, okay? And you'll understand why in a few minutes. But I do want to give you kind of a quick overview on how you solve that problem, okay, for those of you not familiar with this field. So basically there are two main branches, okay? First one is the world of anchor-based methods, okay? So anchor-based methods like SSD, YOLO, and faster RCNN kind of dominate the world of object detection. And it is not surprising that they also work well for the problem of text detection. Basically, text is just an object. But there's actually a more kind of popular approach, which is to use semantic segmentation. Okay, so basically you take your image and you learn a text, no text mapping over that image. And it works pretty well, and one of the reasons it is widely used is because it has better support for polygons and rotated shapes, right? Because, I mean, the text map doesn't know whether it learns a complex shape or just a simple bounding box. You do have to do some post-processing afterwards. Okay, so from now on, for the rest of this talk, we are going to assume we are talking about semantic segmentation approaches. Now, one of the problems with semantic segmentation approaches, especially in text localization, is that they kind of tend to connect words. Okay, so if I have two small words close to one another, and there aren't many background pixels between them, what will happen is that the semantic segmentation will kind of bleed out and connect the words. And again, this is something that is problematic for us. Now, so most of the research nowadays is kind of how to mitigate that, kind of how to make the results more localized. Okay, and this, for example, from a paper called Word Fence. Okay, so you can see how the results go from this to kind of a more localized segmentation. Okay, this is really kind of what makes this research hard in this topic. But again, this is not really our topic. Okay, let's assume now we have a working baseline. Okay, so for example, let's take the EAST method from CVPR 17, which has some really nice results on the ICDR 15 benchmark. Okay, 70% of recall, and it's a pretty hard benchmark. Now, let's say we want to improve that baseline. Okay, well, how can you improve a baseline without doing any work? Well, the go-to solution in object detection is to do multi-scaling. So that's something the EAST method suggested. So what they're doing is they're taking the original image, we're resizing it to make it smaller, to make it larger, and kind of this ensemble of scales help us to get 5% more of recall, which is really important in those kinds of scenarios. Okay, so why does this work? Well, some of you might understand, I mean, without really saying the images, but it goes as follows. So let's say we have this image here, and you see we have a large variability of text size here, okay? So what happens here is that our method is not able to capture the text which is very large or very small. what happens when we resize the image to make it smaller is that we're now able to capture the text which was large, okay? And when we make the image large, we're able to capture the small text. Okay, so basically doing multi-scaling helps us to capture different scales of text, okay? Now, why are we not always doing multi-scaling? Because, I mean, it's expensive, right? So if the original IST method can do about 13 FPS, the IST multi-scale one would do about 3 FPS, which is kind of a bummer if you want to do real-time scenarios, or if you're working with large amounts of data where a factor of 5 can be really important, okay? So can we do anything better? And of course you can improve your baseline. So most of the work nowadays is how can you improve your baseline? So the base method would simply be better. But what we want to tackle here is the problem of how can we really make multi-scaling better, okay? How can we get rid of multi-scaling by staying with the results of multi-scaling? And it's actually a pretty easy solution, and it goes like this, okay? So let's look at this image, and let's look on this map, okay? So what you see here is the raw detection, the raw segmentation result, okay? Before we did the actual post-processing. And you can see that, well, the method is not really able to kind of distinguish the small text regions, okay? For example, the text on the right, it is able to tell us where the text is, okay? So we can kind of tell that, I mean, most of the image here is background pixels, right? And you know for sure these are background pixels. And these are only the regions that are kind of interesting. And when we do kind of regular multi-scaling, blindly multi-scaling, we're kind of wasting a lot of time because we already know, I mean, we already did a single forward pass. We already know which regions might contain text, and we don't really need to do post-processing on the entire image, right? So what we propose is simply to take the image and to filter the background regions. Okay, so this is what it would look like. So we took the regions of interest, the regions that might contain text, and we're creating this kind of compact image. And what we can do now, okay, is to take this image and run multi-scaling on this image. And it might seem like not a big deal, but especially nowadays when many benchmarks and many data sets are sparse, okay, most of the pixels are simply not text, this kind of factor can be really important, okay? So that's kind of the first part. The problem is that we're still doing multi-scaling, right? We're still processing the same pixels again and again. And actually for the small text here, we would only want to scale it up. And for the large text, we only want to scale it down, okay? And the problem is we don't know that, right? We have to do the entire multi-scaling thing before we know what the good results are. Okay, so can we do something a bit better? And we think we can, and it goes as follows. So again, our image, our segmentation map. So we know the text section works well on the right scale, right? We know that we want to make large text smaller and small text larger. We just don't know which regions are small and which regions are large. Okay, for example, look at the region of text here, okay? We know that it says cookery and wines, but theoretically, it could have said something else, like it could have been 4 lines of much smaller text. The network doesn't give us that information. We just have the raw detection result. Now, if the network did give us that information, okay, the scale of each region, things would go and be much simpler, right? Because you could simply scale things to the way you want them to be. And actually, there's no reason the network won't be able to tell us that information. Telling the scale of each row, okay, the pixelic size of each blob or kind of a detection is pretty easy. It's a pretty easy task. It's much easier than actually telling where the text is. Okay, so what we propose is actually to teach a network to output that information. Okay, so what you see here is a network that was trained to also give us the scale information. Okay, so for example, the network tells us that we have a small region here of about 10 pixels per line. And again, this is not the size of the entire blob. This is the size of each row inside that blob. Okay? And now when we have that information, everything becomes much more simple, because what we can do is take the image and create this compact representation. And you see that what we did here is to actually take the text and resize all the text to the desired scale, okay, which is something you can empirically find. Okay? So instead of taking this image here that already saved us the background pixels, we're taking this image and we actually don't need to do multi-scaling, right? We take this image and we only scale once and we are done. Okay, and that's basically the idea. Let's go through it again. You captured it. So we already do a single forward pass. There's no reason to blindly do multi-scaling. Let's capture some information there. Specifically, the blobs of interest, okay, the regions of interest, and the scale of each such region. Okay? And what we can do now is to kind of create a compact representation, and you can see that both the large, average, and small text from the original image is now kind of the same scale. Okay? And this is much easier to work with. Now, what we are doing is we're taking this image, okay? And all we have to do now is to process it again through our network. And if we do a close-up on the window here, you can see that while the single-scale method is able to find the text but not really to separate the different words, our method is now able to do that because, I mean, we scale it to the right size. So everything becomes much more simple. Okay, so that's basically the idea. And what's nice about it is that it's pretty easy to explain, hopefully. Hopefully you've got it. And to implement, okay? So what does it take to actually implement this method? Okay, if you want to try it on your text detection or other object detection algorithm. Well, let's say you have a working baseline network, okay, which has a segmentation head and learns kind of the raw segmentation. All we have to do is to add a scale head, okay, which learns a scale. And the segmentation is trained with some cross-entropy or other smart regularization you might have on your segmentation problem. The scale head is trained with a regression L1 loss. Okay, and that's basically it. Okay, so what we're saying here, we want to know the scale of each region. It's easy, right? The network knows it. We just need to tell it to tell us what the scale is. Okay? So that's a network. Another small problem we kind of want to solve is a packing problem. So we now have all these kind of blobs, okay, all these regions we extracted from the original image, and we want to kind of pack them efficiently, okay, to pass it again through our network. So how can we pack them efficiently? Well, it's actually a classical 2D knapsack problem, okay, with some very smart solutions. Specifically, we use the maximal rectangles best short side algorithm, which, as you can see, can give you really maximal best short side blob, okay, set here. Okay, so this is basically it. You take the blobs, you create this compact representation, and you pass it again through the network. Again, very easy to implement. Now, one thing you may notice is that this image is not really realistic, right? It's not a natural images. And we all know that when faced with out-of-domain images, neural networks results kind of tend to degrade. Okay, so how can we solve that? Well, again, really simple. What we actually did is to kind of create these knapsack images. So we're taking a grant of information. We're kind of stimulating the process of creating these knapsacks, okay, using simple erosion dilation techniques. And what we saw is that the results are significantly improved when the network is also trained on these kind of images. Okay? So basically all you need is to add a scale head and also train on this kind of data. Okay, so that's basically it, and let's see some results. So this is a really nice example from ICDR13, and it looks like an easy example, right? You don't have a lot of text, but text is actually in a couple of different scales. And let's see what happens when we run our baseline method on this image. Okay? Well, you can see the method is able to tell you where the text is, but it's actually not able to correctly localize a small text. Okay? But we know the scale of each region, and this is actually an easy example, right? You could have known it without the scale thing. But now we know the scale of each region, and what we can do is to create this image. Okay, so again, this was our original image. Okay, look at all the text here. Okay, and this is the new image, which is much smaller because most of what we had in the original image is background. Okay, so it's smaller, and all the text is now in the same scale. So when we run our network on this image, actually things become much more simple. Okay, you can see that the network is now able to correctly kind of segment each word. Okay, so again, it's what happens before, and not surprisingly, when the text is large enough, we're able to separate different words. Okay, and this is how the final segmentation would look like. Let's look at this nice example from ICDR15. So we'll look at this region of text and this region here. And what happens when we run our method on it? Well, you can see that it kind of is able to separate the joint pane and the free yourself from, but we're not able to separate the bus lines at all. Okay? So again, we know the scale of each region. Let's create our compact representation, and this is what it would look like. And we can run it again through our network, and not surprisingly, we are not now able to separate each region from the other regions. Okay, so basically the network knows how to segment text, it just needs to get the right text scale. So this is before, okay, you can see we don't have any separation in the areas of interest, and this is after. Okay, so really nice trick, and this is what we get. So how does it compare? Well, let's look at the result of our method and the multi-scale method. Okay, so not surprising, multi-scale method works, right? If we have enough scales, if we have the right scale, we will be able to segment and correctly kind of separate the text. Okay, one of the problems to multiscaling is that we have too many predictions. And doing really a good NMS is kind of difficult. Okay? So this is how it would look like visually. How does it compare on the benchmarks? So we run the ICDR 15 benchmark here. And what we have here is a relatively weak baseline. Okay, it's a very small network of weights about, I think, less than 2 megabytes. Okay, but it is very fast. And what happens here is that it doesn't have really good recall. Now, the multiscale method gets about 20% more recall. And what's nice here is that our method almost has the same recall as the multiscale result. Okay, so in terms of recall, you can see that we are almost as good as multiscaling. Now, what happens in terms of time? Well, not really surprising. The baseline is the fastest of them all. The multiscaling is much slower. Okay, you're seeing both the network time and the total time, which includes the post-processing, which is kind of heavy in segmentation-based method, okay, because you have to do connected components and all such stuff. Anyway, what you can see here is that the method is kind of not that far from the baseline. Okay, so what you can see is that our method lies between the baseline and the multiscaling, both in terms of recall and in terms of runtime. But it's pretty close to multiscaling in terms of recall, and it's pretty close to the baseline in terms of time, which is exactly what we wanted to get here. Okay? So that's basically it. Okay? The take-home message I think from here is that, I mean, if you need to do multiscaling, if you have a multiscaling problem, there's actually no reason to blindly do the multiscaling. Okay? You can use the single forward pass you already did to kind of take these images, okay, these relatively large images, and create really compact representation, which are much easier to work with. Again, we believe this is something that can also be useful for other text detection and object detection algorithms. We're hoping to release our code soon, so we encourage you to kind of give us a try and tell us how it works for you. And that's basically it. Thank you.